Hello guys, welcome back. So this will probably be the last video on the series of videos on gravity. So in this video I have been talking about various concepts on gravity and the other stuff, the definitions, equations, derivations, solutions, every other things on gravity. So in this video I will be talking about a relationship. Now I talked about relationship between different quantities and rotational motion as well. So if you are not well versed with that, I invite you to watch that, but that will not actually have an effect on this one. I am just saying as an example. So in rotational motion we derive relationship between the translational quantities and the rotational quantities. Now in this video I have been deriving a relationship between the gravitational quantities itself. Both the quantities will be gravitation. So the first quantity I will be taking is the field strength, and I will be deriving a relationship of between field strength and the potential gradient, right? So you know these terms, right? You know what is meant by potential field strength, and you know what is meant by potential gradient if you have followed up the videos, my series of videos on gravity. So in this video I will be drawing up a relationship between these two gravitational quantities. Alright. So the relationship between field strength and potential gradient. Relationship between relationship between field strength and potential gradient. Alright, so that's the topic of this video. Alright, now if I take a mass in a gravitational field from point A to B, and the distance between these 2 points to be, I take a very small distance to be delta r, right? Delta r, because it's a very small distance. I'll take the value of delta. Now you know why delta is used. Delta is used for very minute quantities. Delta m, which is a very small mass, is a very minute mass. Delta v to be the change in the velocity, so that will be also minute value, and delta a to be the change in acceleration, so on. So the change in distance, since it's a small distance, I will not take the value to be r, I will take the value to be delta r. So I will take 2 points A and B in a gravitational field, A and B in a gravitational field, and the distance between these 2 points to be delta r, right? Delta r. So the work done per kilogram, now say this object is 2 kilograms, so work done per kilogram, so that is actually the value we are taking, that the field strength, right, or the average field strength. So the work done per kilogram, I will find that work done per kilogram. I'll tell you why I took this, right? I'll tell you later in this video why I took this. Work done per kilogram is equal to force done per kilogram. Force done per, right, not this by, right, this per, right, per kilogram. Force done per kilogram times this distance. Now because you know W equals Fd, right? W equals Fd. So the work done per kilogram should be force done per kilogram times the displacement of this work, displacement of this object. So the displacement of this object is from A to B, and the displacement is delta r. So this multiplied by delta r. So that's the equation. Alright. So what is the force done per, now in order to find the work done per kilogram, you need to find the force done per kilogram. So what is the force done per kilogram in moving this mass from A to B? So force done per kilogram, force done per kilogram is equal to what? So the force done per kilogram is, now you know from the previous videos that the force divided by kilogram, right, which is the value of F divided by M, is actually equal to E, right? Actually equal to E, because the field strength or the field, right? Field strength is equal to the ratio of force per mass. So force done per kilogram is, right, force done per kilogram is actually value of E, or which is equal to, right, which is also equal to the field strength. Field strength means the average field strength, right? Average field strength, because the field strength varies. Field strength varies because I have not taken this distance B to be directly away, so the field strength varies because it's an angular, not in a vertical direction. So I'll take the average field strength in the AB region, strength in the AB region, right, in the AB region. Alright, so the force done per kilogram is equal to the average field strength in the AB region. So that's the reason as to why I took work done per kilogram, because in order to make a relationship, I need the value of E, right? I need the value of E, which is the field strength here. I need the value of potential gradient, which is the gradient divided by the distance. So in order to find the field strength, on the vice versa, I would find the average field strength in the AB region is equal to the force done per kilogram. So in order to make a relationship, if I know the value of force done per kilogram, I can find the value of work done per kilogram, and then I can build up a relationship between the field strength and the potential gradient. So that is the reason as to why I took work done per kilogram, not the work done by this object. Okay. So force done per kilogram is equal to E over the average field strength in the AB region. So work done, work done will be equal to E times, so the work done per kilogram is equal to the force done per kilogram. So you can substitute the value of E in place of force done per kilogram here. So the work done is equal to the force done per kilogram, which is the average field strength, times the displacement delta R, right? So work done per kilogram is equal to E times delta R. So E times delta R is equal to delta V, right? So it's very simple now. E times delta R is V, because E is equal to V by R, or delta is equal to delta V by R, right? You know that. So delta is equal to delta V by R. So E times delta R, or delta E times R, is equal to delta V. Alright, so the work done is equal to delta V. So what you can find here is that what you should know here is E times delta R is equal to delta V. So we are actually drawing a relationship between the field strength and the potential gradient. So the field strength is E, and the potential gradient is the gradient. Gradient means the potential divided by the distance. So the potential is delta V and the distance is delta R. So the potential gradient is delta V by delta R. So what we have to do is on one side we have to create the field strength. So field strength has been already created, E, but we have to create the potential gradient. So what I'll do is that I'll divide this by delta R, because delta R cannot be 0. If delta R is 0, A will coincide with B. So if delta R is not 0, we can divide both sides by delta R. So this delta R divided by delta R is equal to 1. So that multiplied by E will be equal to E here, which is equal to delta V by delta R, right? So what it actually happens is that field strength in gravitation, or field strength under gravity, is equal to potential gradient. But this is not so in practical situations. So when the potential decreases, the value of R increases. But when the potential decreases, the value of R increases. So is actually, so this can be also said that delta V by delta R. So what you can say is that limits in from x equals 0, when x approaches R, E is equal to limits when x approaches R delta V by delta R. So E is actually equal to dv by dr is actually equal to dv by dr from limits. So since the value of r increases when the potential decreases, there's actually a negative relationship. So E is not equal to dv by dr, but E is equal to minus dv by dr. So in magnitude the potential the field strength is equal to the potential gradient, but if you are taking since field strength is a vector, it's actually not equal to the potential gradient in direction. It's actually in the opposite direction, or the work is done actually by the external agent. So E is equal to minus dv by dr. So that's the relationship between field strength and potential gradient. And I will see you with another topic on physics through the next video. See you then.